Hi, we are group 5, and our topic is steel connections and probability in civil engineering. Our group members are me, my name is Caroline, and we have Griffin, Sebastian, Eric, and Ali. Our project explores risks and quality measurement in steel connections, which is a key topic in civil engineering. The importance of steel connections. So steel connections form the foundation of structural stability in bridges, buildings, and other large-scale projects, and their performance depends on two main processes, bolting and welding. Both must meet strict quality standards to ensure safety, yet in real-world conditions, these two steps often influence one another. For instance, a misalignment or improper torque during bolting can make welding more difficult or introduce stress that lead to future defects. This observation led us to our central question. If a bolting defect occurs, how much more likely is that a welding effect will also appear? To study this, we are using conditional probability, a concept from our statistics course, to examine whether these two types of defects are truly independent or they're correlated. By applying a statistic analysis to a realistic engineering problem, our goal is to better understand how quality control issues spread across the construction process. This insight can help engineers design more reliable inspection methods, reduce risks, and ultimately improve the safety and durability.
Hello, this is Sebastian. I'll be doing Section 2, Background and Data. To begin our analysis, we first establish our core variables. The discrete random variable x and y were established, reflecting quality failures in bolting and welding respectively. Each variable uses three levels, 0 meaning good, 1 meaning minor defect, and 2 meaning a severe structural level defect. The data is presented in the PMF table. This table represents the probability of every combination of bolting and welding defects occurring together, based directly on site quality measurements, which will be the key input for our statistical model. Now, if we take a look at the bottom right corner of the table, we can see where x equals 2 and y equals 2. It shows that the value is 0.08. This is the raw probability of having a dual severe failure. This is the joint probability, and we can use this number for the conditional probability to analyze amplified risk of welding failures when bolting has already failed.
Hello, my name is Eric, and I'll be doing the methodology part. To begin our analysis, we define two discrete random variables, x and y. X represents the quality outcomes for the bolting process, and y represents the outcomes for welding. Each variable is grouped into three levels based on what we observed on site. Level 0 indicates good quality, meaning the work meets acceptable or optimal standards. Level 1 is a minor defect, referring to small issues that aren't structurally significant. And level 2 represents a severe defect, which signals major structural flaws that require immediate attention. By categorizing the data this way, we're able to analyze the quality performance of both processes in a consistent and meaningful way.
Hello, this is Griffin Keela, and I'm doing the results section. And from the PMF table you saw in the slide previous, there is a clear correlation between the failures of bolting leading down to more failures of welding. If you check an independence test using what we learned in statistics, you will see that there's actually a fourth of what it would be if they were truly independent of each other. The fact that the observed is 4 times when the bolt failures happen, there's a 4 times likely chance that a welding failure happens. There is a clear correlation between the two. And some solutions for this would really mainly just be improving quality control, especially at the beginning of the process. Having inspectors come in and making sure everything is up to code while the bolting is happening will prevent trickle-down effects of welding failures in the future. So make sure everything is working correctly.
Hey everybody, this is Ali. I'm doing the engineering implications and the conclusion for this project. So the findings from our joint probability analysis show that bolting and welding defects are not independent processes, and that severe bolting defects greatly increase the likelihood of severe welding defects occurring. And so this relationship highlights several key engineering implications. First one being the quality control. It must be proactive and not reactive, where catching the alignment or torque problems early in bolting prevents costly welding issues later in the sequence. Second one being inspection sequencing becomes critical, which the engineering teams may need mandatory bolt quality verifications before welding operations can actually proceed. Third is training and standardization should focus on bolting crews. Since bolting errors have a compounding effect, improved skill and oversight at this stage can yield major reliability gains. The fourth is structural safety margins depend on connected processes, and so this is it's not enough to ensure one process meets standards. Engineers must manage the interactions between processes to avoid cascading defects. And the last one is just the better risk models for a steel connection. In general, our data shows that extreme failures are more common than predicted under independence. So this supports developing correlated risk models for use in design specifications. So in conclusion, through statistical analysis of real-world quality data, our project demonstrates a clear correlation between bolting and welding defects in steel connections. The observed joint probability of dual severe failures, which is 8%, is nearly 4 times higher than the 2.2% expected if the processes were independent. This amplified risk shows that errors introduced during bolting can propagate forward negatively, affecting welding performance and compromising structural safety. So, by applying conditional probability to a civil engineering process, we can better understand how defects spread and where quality control resources should be focused. So, the key takeaway is actually clear. Better bolting practices lead directly to safer and more reliable welded steel structures. And so this insight can be used by engineers to improve inspection strategies and reduce rework, strengthen safety margins, and extend the service life of steel infrastructure. Thank you so much for listening. Thank you.